Hello, everyone. Welcome back to these short tutorials on how to use BioFlow. These are informal tutorials that help you to use the different analytical modules by providing some guidance. And in the past videos, we show you how to retrieve the new data and how to retrieve all the analysis and saving as you move throughout the pipeline. And in the past videos, we also showed you how to QA your phenotypes and genotypes, how to do single trial analysis, how to run an MTA with markers, with weather information, how to fit selection indices. And now the focus of this module will be on the optimal cross-selection. So we're going to assume that you already looked at the previous videos. If you have not, please go to the description and look for the previews. And for that, I'm going to start retrieving the old analysis that we fitted in the past tutorial where we did a selection index. So I'm going to load it by going to data management, retrieve all the analysis, browsing your file, and then clicking on load objects. Then you will receive that OK message or success message. Then I can go to the optimal cross selection module, and you can see that in the information tab, I have a good or complete status message that my data is good to go to perform OCS. In order to perform OCS or optimal cross-selection, you have to go through all the other modules. You need to QA your data, you need to do STA, you need to do MTA, you need to do an index, and then you can do optimal cross-selection. And that is because the input of the OCS module is a timestamp of an index or a selection index. The timestamp that we're going to pick is the one that the only index that we currently have available. You can see that the index is showing here that it comes from this MTA, and this MTA comes from this STA. And there was another two MTAs that were done, but that they didn't lead to anything else. And this STA comes from QA in the raw phenotypes. So there's no more to select, so I'm just going to pick this one. Remember that all the modules have this information tab, this input tab, and this output tab. So now I can move and pick the trait. The trait is, of course, a desired index, and you have to decide what materials should be used for the optimal cross-selection. Remember that the optimal cross-selection aims to take the merit of the individuals for the index and make the best possible crosses. And you will decide, of course, the number of crosses and how aggressive you want to be in the trade-off between genetic variance and performance. But first, let's go step by step. You pick the selection index analysis to use. When it comes to the traits, you pick the sire index. When it's asking you what entries you should use, you have multiple ones. You have GBBs from materials that were predicted, but maybe for another trait they were also tested. GBBs for materials that were predicted, but in some other traits might have shown as different with a different label, like unknown. And you have, GBBs that materials that were totally tested in both traits or in all the traits from the index. And then you also have materials that have no marker information, so they were only the total genetic values. So for this particular case, we're going to skip using the TGBs. So materials that don't have marker information, we will skip them. So we have 780 materials, that are available for the crosses. And then I can move to the next section, which is setting the contribution parameters. And the default is to make 70 crosses, but you can do less or more. I'm going to pick, let's say 50 crosses. So I want to get the best 50 crosses between all these 700 materials. And in the target angle, this is how aggressive you want to be in your contribution parameters. For example, we know from this figure that the lower the degree, it means more weight into the performance, and the greater the degree is more weight into the genetic variance, let's say. So you are more worried about keeping genetic variance. A good rule of thumb is to pick the degree of 30 or 30 degrees, which is a good trade-off between good performance, but also making sure that we do not select many sister lines, and that we are ensuring that the breeding program can run for several generations. But if you are an expert on this area, you may want to fine tune the target angle. The relationship to use, we are picking the GRM because we have market information. That's the default. But you can also use the numerator relationship matrix if you have a pedigree, or use a combination of both. So once you have set the contribution, so you saw I fitted or I set to 50 crosses with an angle of, let's be a bit more aggressive and go for 20. Then you can go and click on run analysis. And you will see that there is some additional run settings. In case you feel familiar with the OCS algorithms, you can define the stopping criteria, the maximum number of individuals to use, and different other parameters. So I will just click on run OCS, and I will give some time for the optimal contribution selection algorithm to find what are the best 50 crosses between all those materials that I provided. So you can see that it finished and it took me to the output tab where I have the predictions. And in this case, I have predictions for crosses where it's asking me to cross this mother and this father. And it's assigning a name that is just the name of the cross. And it's telling me that, this is the predicted value of that cross for the index, which you might remember didn't have much meaning, the index, but it's telling you that that is the best cross. And of course, there is 50 crosses because I asked 50 crosses. There is also metrics, that is using to tell me that, this is is storing an environment, let's say what I specified, that I wanted to use a desired index and give me 50 crosses with 20 degrees. Some of the modeling parameters, what was the formula that was used, and what was the input object. And it's also producing a dashboard, which is very useful because it provides you with the crosses that it has, created for you. As we said, is the 50 crosses that you requested. It's also predicting for you what is the yield of that cross, the grain moisture of that cross, and as long as those materials were present in the MTA analysis. Also, it will show you some of the number of crosses per parent, because, even though you did 50 crosses, this is showing you which parents are being selected most of the times to achieve that target. You can see that this parent probably has a very good contribution, either for variance or for performance, and that's why it's being used many times, whereas there is some parents that are used less times. In this case, you don't have to worry of how many times a parent is being used, because you have already specified what is the trade-off that you are willing to have. Even though this is selected multiple times, it means that it still is able to achieve the target that you set in 20 degrees, which is a strong weight on performance and a bit less on genetic variance. If I had selected less stringent and I had put, let's say, 90 degrees, I would have probably more materials and each material showing up less times. And I can show it in a minute. You also get the performance table of the parents that, all these parents that are being picked from the 780 materials that you had, only these materials were picked, which is 19 parents. And then you can see what is the performance for the different traits. And you can also see if there was any difference between if you have more treatments. In this case, we only had one treatment, 50 crosses and 20 degrees. And it can also show you for the different traits, in this case, the grain yield and moisture, the performance of each parent. So this parent has maybe greater performance than any other parent when it comes to the crosses. So this is what comes out from the OCS algorithm. You can always download the dashboard and explore it a bit more and share it in the advancement meeting on how you came up with those crosses. Just keep in mind that the most important part for deciding your crosses is in these input set contribution parameters. So this is the step that would allow you to create the crosses for your crossing block. You can see that now, just for the sake of showing something different, I'm putting 90 degrees, which is very low weight on the genetic variance. Sorry, on the performance, and a lot of weight in the genetic variance, which means that now we should have probably more parents selected and parents showing up less times. You can see that it finished, and I'm gonna move quickly to this plot, and you can see that now we have many, many more parents, and each parent is showing less times. Now there is 45 different parents. Before there was 19. So I hope this helps you to understand a bit more the foundations of OCS. Otherwise, you can also look at the details in the information tab and some of the references and the code that is being used behind the scenes. If you have any additional questions, don't hesitate to contact us in the go into the home tab, about us section, contact and development, and support desk. Also, don't forget to save your analysis. If you're needing to close the application, you can just go to data management, save analysis, assign a name to your analysis, and click on save. That way you can close the application and come back later and start where you stopped. I hope this was useful, and good luck with your analysis.